We can play games all the time.
Okay.
Let's play a math game.
Okay,
The math game is,
this gonna take the whole time?
let's suppose that San Jose is experiencing exponential growth of its population. It's a great game. Okay? In 1990, the population of San Jose was approximately 782,000 people. And in 2000, it had grown to 895,000 people.
Whoa.
Okay? So, what I'm asking you to do right now is I am asking you to come up with 2 ordered pairs, so 2 points, based off of those 2 sentences.
That was disgusting.
And justify it for me. Come up with 2 equations, or not 2 equations, excuse me, 2 points that fit those 2 sentences. One point. Give me one. Give me one of them. 0, comma what? Okay, so explain to me why you chose 0, comma 782.
Because we're going to use like 1990 as a starting point.
Okay.
And then I said 72 because I didn't want to write out 782,000.
Okay, right? Okay. So looking forward, looking down this page in your blue packet, side note, we're going to be in your blue packet today for this first page, and then we're going to be just in regular notes after that. Okay? So if we do 0, comma 782, and I look down that page, I shouldn't say preferably, most importantly, when I get to letter D and I sketch the graph of this, what is going to be the label on my vertical axis? People in thousands, or population in thousands is going to be that label on that graph. And which is nice because then our numbers are a little smaller, okay? More easy to deal with. Okay, love it. So if we base our first point as 0, comma 782, what is our second point? 10, comma 895. Because 10 would be because 2000 is 10 years after 1990, and 895, we would divide 895,000 by 1,000 and get 895. Okay, love it. Now, using those 2 data points, I want you to find me an experimental model in the form P of t equals a times b to the t power, where t is the time in years, and a represents my initial population, where t is equal to 0. Go for it.
Yeah. Yeah. Okay.
Do I know A?
Yes.
What is it? Why do I know that A is 782? Two ways. One, it told me right in the problem that A is the initial population where t is equal to 0. and we found where t is equal to 0. Okay, and we have it set up that way. Or 2, I could plug in the point 0, 782, and I would say 782 equals a times b to the 0 power, and b to the 0 power is 1, which just leaves me with a as 782. Okay. So right off the start, I know that this function is going to be 782 times something to the t power. How do I go about finding b? I already did one, so now I got to plug in the other one. Okay? So again, I reset myself with p of t equals a. Oops, I know what a is now. A is 782 times b to the t power. So then this would be 895 equals 782 times b to the 10th power. How am I going to solve that for b? First, I'm going to divide by 782. Now what? Take the 10th root of both sides. When I take the 10th root of 895, divided by 782, I get 1.01359. Really, I get 1.0135883920064. So this is 1.01359. So there is my exponential model in the form a times b to the t power. Part C. Using our model, which our model again was p of t equals 782 times 1.01359 to the t power. I want you to now figure out how many people live in San Jose in 2005. What year am I finding data for? What? Why 15 and not 2005?
Because from 1990 to 2005 is 15 years.
15 years. Yep, so I'm actually finding P of 15. When you plug in P of 15, what do you get? 957.506 is what I had heard. Do we agree with 950 that there are 957 people living in San Jose in 2005? So add your zeros for me.
Do you round that to 958?
I wouldn't round it, no.
957,000.
I'd go even more than that.
I don't know.
So
Wait, that doesn't make sense.
exactly. That's my point. So 957.506 is what we've got up here, right? But what is that? In thousands. So what do I have to do with this number? Move the decimal place. How many spots? 3 to the right. So one answer that you could possibly get is 957. What did you say? 506? 506. Okay? The answer I got is 782 times b to the 15th times. I got 957,483. Why the discrepancy? And what did I do? No, I took the exact value of b. Yep. I stored my b here in my calculator as b. Okay. What? How do we do that? Control var. Okay. So I stored b as b, and then used it as b in the problem down here. Okay. And mine then was a little more exact than yours because you rounded yours. Not saying that there's anything wrong with that, okay? Because we did go out to 5 decimal places, okay? Yeah, okay. Right. We want to be as exact as we can, okay? All right, did I say 483? You have it already. Okay. Now, we want to graph that scenario on an axis. So, graph it for me, and then I want you to label your axes. Okay, so there's my general picture. Yes? We just got to throw some more labels on it. Okay? So, give me something that I can label. Population in thousands on vertical or on horizontal? Vertical. Okay, so populations in thousands on my vertical, and then I probably want to throw one on there, right? Or a couple of numbers on there. Yeah. So right here would be 782 because I know that one. And then let's go up here as 895. Okay, love it. 2 of the 4 labels are labeled. Time in years as on the bottom then. Just in years. Right, so how would I label it? That's what I like. Time in years since 1990. Or years after 1990. The more specific we can be, the better. Okay? The more specific that we can be with our labels, the easier it is, the more information we can get out of it. Okay? And then we would label this obviously as year 0, and then this would be year 10. With me? Hmm? I don't know.
Is it okay?
Is it exponential?
Yes.
Is it growing?
Mm-hmm.
You're good. Do you have the label?
Yes.
Numbers?
Yeah.
Then you're good. Okay. Next question says, using our graph, we want to figure out when the population is going to be 1 million people. It's an Austin Powers thing. Probably too young to even know what Austin Powers is. Yeah. Levels here. So how am I going to do that? Plug in what? So I'm gonna make myself a graph first. What's my graph going to be? The equation, the function, the 782 one? That one? Instead of t? Why? Because this function is in terms of x. So I can't type it in just exactly as is. I've got to type it in with a variable of x there. Shabam, there it is. Oh, no, guess what? Got to change my window, right? Okay. Can't see it. Okay. Menu, window, window settings, boom. Okay, so now let's talk to me about my graph. What does negative x's mean? Years before 1990. Do I care about years before 1990 right now? No, I might later on, but right now I like to go negative 5 there. Years after 1990 would be the positive x's then. How far out do we want to go? What you got? 30? Okay, love it. I'm going to go by 5s. Okay. I know I got to go at least 10 because at 10 I was only at 895,000. So I got to go more than 10 for sure. Okay. So we'll go 30. Love it. Excited to be part of it. Okay. Y's. What's the Y's?
Good one. The Y's.
That's population, right?
That's a big number.
Can I be negative on population?
No.
Heck to the no. Okay. But I am going to, just for sake of, I like to see my axes. That's why I go negative yet there. Okay. Now, I need to get to 1 million on population. So do I type in 1 million there? No. What's the biggest that or what's 1 million on my graph? 1,000. So I need to go somewhere above 1,000, right? Okay. 2,000? 3,000? How about 1,500?
Oh, come on.
And there I'm going to go by hundreds.
Wow. How neat is that?
Okay. So there's my exponential. It doesn't really look exponential, but if we zoomed out a little bit more, shabam, it would be there. Now, what do I want to do?
Put in a line.
Which line?
At 1,000.
At 1,000, right? Yep. Okay. So I'm going to put in a second function, and it's going to be 1,000 because that's when my graph was at 1,000,000 people, or when the population of San Jose is at 1,000,000 people. Okay. Love it. Now, my next question to you is this. What if our graph
Are we gonna find a new
ended up looking like that?
Yes.
We'd have to slide it over until we found that intersection point. We just so happened to be smart about it, and we found a range where we had the intersection point in there. Okay? So now what? How do I find that intersection point?
Put it in there.
Menu,
Do it.
analyze graph, intersection.
The sniffles came.
The sniffles have come. Okay? So I get that. Now my question to you is this. Oops, I need that on there yet. Is this. When will it surpass 1,000,000 people? So in 18.2 years, right? From what?
1990.
From 1990. So that is 2008. Now, 0.2 of a year. That's going to be what?
February.
February-ish?
Yeah.
Yeah? Late February, early March, somewhere in that range? Okay? Of 2008. Okay? Love it. What I would like you to do now is I would like you... What's up?
Like on the point when we found it was 1 plus 3, that's just it's 1,000.
That's 1,000. Yep. So I want you to find when Columbus, Ohio is going to exceed 800,000 people. So I would say that this is the point 0, 633, and this is the point 10, 711. So my A value would be 633, 711, 633, B to the 10th. So the 10th root of 711 divided by 633 is going to be B, which is going to be approximately the 10th root of approximately 1.01169. Right?
Wait, so what is this the answer?
I don't know, I haven't gotten that far yet. Okay? So the
Oh, we have to use the graph.
P of T is going to be 633 times 1.01169 to the T power. So now we have to graph that. Let me change around my 711 divided by 633. Okay, so there's B, which is, that's what we want. Okay, and then now this should have changed. Yep, and then I need to change this to, instead of 1,000, this needs to change to 800. What? Oh. Yep. Yep. And then this one has to change to, whoa, tap the brakes. Go back over here. It's easier over here. 633 gets me there. Okay.
Is it still? Oh wait, no, it's not 1,000 anymore.
Nope, it's 800 now. Right?
Didn't know it did that. What's the y-axis or the x-axis?
So 20 years from 1990 would be 2010. And probably early 2010 again, right?
Yeah, it's 20.1.
Okay?
2000 what?
10.
Yes.
This is 20 years after 1990.
Yes.
Nicely done. Okay? All right. We are done with the blue packet for now. Just know that there are homework problems on the last 2 sheets of that blue packet that you could be doing at any point in time now. Okay?
Well, obviously we have homework for like
Yep.
stuff being collected like this.
We haven't decided yet.
Okay. So I
We'll let you know. Okay?
like the last 2 pages.
The last 2 pages.
How much should we know?
I'll tell you that later.
Hey.
Okay? All right. So this is out of your notes now.
We're still going?
Yep, we're still going.
We're still
Yep.
talking.
Huh?
Okay? So suppose you rake your yard. And before you get the rake hung up in the garage, there are 50 leaves that are on the ground. So you turned around and poof, there were 50 leaves on the ground. The number of leaves continues to increase by 8% each hour. So let's say you got done raking leaves. You decide, I'm going to go inside. I'm going to grab myself a quick sandwich. Okay? So 1 hour later, how many leaves are now on the ground? How many leaves are on the ground 1 hour later? How many leaves are on the ground 1 hour later? 54. Give me one way that you can come up with 54. Go ahead, Ted.
Take your starting amount of leaves
Okay.
times by 1.08.
Okay.
Yeah, 1.08.
And so 1.08 times 50 is 54. Yep. Love it. Give me another way to get 54.
50 is half of 100, so 8% of 100 is 8, so then half of that is 4, so it's 54.
Okay. So basically I'm thinking what you're saying just in a different way is you took 50 and you multiplied it by 0.08. Right? And you got 4. But then you had to add back the original 50 that were on the ground. So that's how you got 54. Okay? Okay? That's one way of doing it. Okay? The other way that we had already said too was we could have done 50 times 1.08 and gotten 54. Okay, because that adds in that, it automatically adds in that 50. Okay, so let's say lunch turned into, oh, you were sitting on the couch and you took a little bit of a nap because you worked hard all morning, right? Okay, so now it's 2 hours after you got done, and how many leaves are on the ground? How many leaves are now on the ground? I don't know, but how many leaves that is?
I don't know if I did it right.
What'd you get? Yeah, no. How many you got? 0.32? Because you took 54 times 1.08, right? Okay, but 54 was 50 times 1.08, right? Let's say you couldn't wake up from your nap, and then an hour later your kids come and jump on you. Happens all the time. Now, how many leaves are on the ground? How many on the ground? Pretty close to 63, right? 62.9856, right? Because you're counting the number of leaves that are on the ground.
Yeah.
Yeah, if 8%. What? Nope. Because they're increasing by 8%. So it's the increase is increasing too. Yeah. Yeah, what? Because we're not there yet. We're getting there. Yeah. Yeah. Okay. So, 12 hours later, how many leaves are on the ground? That's the final question. After 12 hours, how many leaves are on the ground?
Oh my god. Do you draw your bottom part and then cross it? Or do you like, okay, yeah. I've like tried to do it.
How many we got? 126. Really, it's 125.909. But we'll probably call that 126. How did I get that? That's a great question. How'd you get that? Because like this one up here, so this hour number 3 would have been 58.32 times 1.08, right? Which 58.32 was 50 times 1.08 times 1.08. So then this would be 50 times 1.08 to the third power. Right? which means this one down here would be 50 times 1.08 to the 12th power. Okay? So what we're doing is we're using a population type model. Okay? Now this is basic because it's not continuous. Okay? This is only changing once every time frame. Okay? So P of t is equal to P sub 0, where P sub 0 is your initial amount. Starting value, initial amount, however you want to call it. Times 1 plus or minus r, plus obviously if we are increasing, compounding, what's the other word I'm looking for? Appreciating, growing in value. Okay, minus if we're depreciating, decomposing, decaying, whatever you want to call it. Okay, and t is our time. Now we said time in years there, but time really here is, however, whatever time frame that our problem is set up for. Okay, we used it in the last problem as hours. We can use it most of the time. We'll use it as years. But it's whatever the time frame of your problem is set up for. Okay? So, 2 problems to go here now. So, determine the exponential function with an initial value of 12 and increasing at a rate of 3.5% per year. Okay? So, we want that in P of t form equals P sub 0 times 1 plus or minus r to the t power. Okay, that's our equation. So this would be, then, this function, this model, would be P of t equals what? 12 times 1 plus 3.5%. That's a cool cloud. Cool, like shelf cloud right there. Yeah. Okay. You gotta come out.
You have to look at it.
Yeah, you gotta come out here to see it. You gotta come around the corner.
No one can get up and look at it.
Exactly. Yeah. So 3.5% in decimal form is what? 0.035, right? So this would be 1.035 to the t power. What if it were decreasing by 3.5%? 0.965, right? Okay, 0.965 to the t power. Okay? All right. So, way back in 1985, you were aspiring mathematics teacher at Wausau West High School living in Duluth, Minnesota. Okay? You purchased a 1979 Ford Pinto back in 1985. I didn't grow up in Duluth. But she is not here right now.
That's her.
No.
Okay? Valued at $1,800. This Pinto, classic. Okay? White with red striping, Starsky and Hutch style. Okay? And sport rims. It was all the talk of Greenway High School in Duluth. Okay? Hard to believe, but somehow this hot rod actually lost value at a rate of 7% each year. Okay? What I would like you to do is I would like you to find an exponential function, an exponential model, that describes the value of this classic as a function of t in years since 1985, and then find the value of the Pinto in 1990. Spot check here. What do we got for a equation, an exponential function? We'll call it P of t. What do we got for P of t? Okay. Times what?
Times
Okay, so could I write that as 0.93
Yes.
to the t power? Okay, right? Because we can do that 1 minus 0.07. Okay, and then what did we get for a value in 1990? $1,252.24, because we can go out to the cents on this one because it's money. Okay. If it were today, I will tell you this, because I did this while I was waiting on you guys. If it were 2019, that would be year 34, and the value of this hot rod car right now would be a whopping $152.65. I bet you the metal inside of it is worth more than that. So it would require a lot of repairs. It would probably be pretty rusted. Yeah. Yep.
More expensive.
Yep. So again, in your blue packet, those last 2 pages, those are your homework problems for the first couple of sections. You can do some of them, but you can't do all of them yet. Okay. So if I was looking at them, you could do number 1 and 2. You could do number 4.
Yes.
You could do number 5.
What about number 3?
What about number 3?